All right, we're recording in live. So, Zach, you're good to take it off whenever you want to.
Okay, great. I'm just going to very quickly minimize this. Okay. So welcome, everyone. Thanks for showing up. So Parsa, let's make sure that recording. Welcome, everyone, to the 2024 Turing Award winner speaker series at the Georgia Institute of Technology, College Computing, sponsored by AI2 Incubator. During the course of the semester, 5 Turing Award winners, 1 Nobel laureate in physics, and many other famous computer scientists will be speaking and giving presentations to 2,000 plus RSVP'd students and faculty from the top computer science universities in the world. Thank you very much to our esteemed speaker series advisors, Dr. Shvi Galil and Dr. Bjarne Sestrap, for helping make this initiative a reality. I'm so grateful for your advice and guidance as we plan this tremendous speaker series. Thank you as well to our favorite LinkedIn influencer and sponsor, Aish Sarvazian, for her assistance with helping market the series to her 485,000 plus LinkedIn followers. We simply could not have achieved our stellar attendance numbers without you. I'm extremely excited to announce the insanely accomplished computer scientist and the winner of the Turing Award, Dr. Barbara Liskov. Just give me 1 second here. Okay. So Dr. Liskov is an American computer scientist who has made pioneering contributions to programming languages and distributed computing. Her notable work includes the introduction of abstract data types and the accompanying principle of data abstraction, along with the Liskov substitution principle, which applies these ideas to object-oriented programming, subtyping, and inheritance. Her work was recognized with the 2008 Turing Award, the highest distinction in computer science. Dr. Liskov is one of the earliest women to have been granted a doctorate in computer science in the United States, and the second woman to receive the Turing Award. She's currently an institute professor and the Ford Professor of Engineering at the Massachusetts Institute of Technology. So now let's take it into presentation mode. Without further ado, I give you all Dr. Barbara Liskov, and now I will make this screen share bigger again. And Parsa, if you could let me know if can people see the?
Yep, looks perfect.
Cool.
Okay, so now you can hear me, right?
Yes.
Okay. All right. Thank you so much for that kind introduction. I'm going to talk today about data abstraction. And I'm going to start, if you could show the next slide,
Yep.
With just a little bit of how I got into computer science in the first place. I did my undergraduate work at the University of California in Berkeley, and I majored in math. And when I graduated, I decided to get a job, and I wanted a job that would take advantage of my math skills. And I was offered a job as a programmer. And at that time, I didn't even know about computers. I knew nothing about programming. But also at that time, of course, there were no computer science majors. So companies needed programmers, and they were taking a chance on people like me where they thought, even without the background, maybe we could do the work. So that's how I got into computer science, completely by accident, because I got offered this job that seemed like it might be interesting. And my first day on the job, I was handed a Fortran manual and asked to write a little program. And I discovered a field that I thought was fascinating and that also sort of matched my abilities. So I worked for 2 years, and then I decided to get a PhD. I was completely self-trained. It seemed like maybe I could learn a bit faster if I had some courses to take. And I went to Stanford, where I worked with John McCarthy. And I did my thesis in AI, a program to play chess endgames. At that time, chess was a very challenging AI problem because computers were very small and slow, and chess required a lot of search. And since we couldn't search very much, we had to find all sorts of clever heuristics to get around the problem. And endgames required different types of heuristics than the other parts of chess, so that's what I was focused on. Of course, this is a long time ago and things have changed a lot. When I finished, can you go on to the next slide, please?
Yep.
when I finished at Stanford, I went back to work at the company that had hired me initially after my bachelor's degree, the MITRE Corporation in Bedford, Massachusetts. Only now I was going to be a researcher, not a programmer. And I also made a switch at that point out of AI and into software systems. I had decided at Stanford that I wanted to make that change, but I decided to wait until after I got my PhD since I was already well along on that path. My first assignment at MITRE had to do with, MITRE does research for the government, so we were working on various research topics that they were interested in. And the first one had to do with an evaluation of microcode, which was a big deal at the time, and then follow up on designing and implementing a time-sharing system, which was actually a research topic at the time. And that took up my first couple of years at MITRE. And then, next slide, I was asked to look into the software crisis. And the software crisis is not anything you hear about today, but it was a big deal at the time. The problem was that even though the software systems that were being built then were much smaller than what we have today, they were still much bigger than people knew how to manage. So maybe they were 100,000 lines of code rather than millions of lines of code. Still very big. And people did not know how to build software systems that worked. And it was very common in the 70s, the 60s, even up into the 80s to pick up the newspaper, and in the business section, you'd see an article about some company that had spent millions of dollars and hundreds of man years building some software system that had to be discarded because it simply didn't work. So this was really a very important problem. If you can go to the next slide. Yep, which I just explained. So now we can go right on.
Next
and
slide.
Next slide, please. And what it did was it got me into the field of programming methodology. So of course, what I did in going to a field I knew nothing about was I started searching around for the literature, and I discovered this field of programming methodology that was focused on this very important question. I mean, you really had to figure out how to build software systems. And so I started reading the literature, and I discovered that there were papers talking mostly about two related but different topics. One of them had to do with the design problem. How do you design a program so that you end up with something that works? And the other one had to do with just a fundamental question of what is the structure of programs anyway? And people were talking about something they referred to as modularity, where the idea was a module was a kind of a black box where you didn't really know what was going on inside, but you could use it to accomplish something. And that was kind of what they knew about. Next slide, please. Okay, so what I'm going to do now is just describe a couple of the papers I read, and then I'll come back to this modularity question. The first is a very famous article by Dijkstra. It wasn't actually an article, it was just a letter to the communications of the ACM, written, as you can see, a long time ago. Go-to statement considered harmful. And it probably seems very strange to people who are writing programs today that there would even be an argument about such a thing, because after all the languages we use today do not have go-to statements in them. You do everything through well-structured control structures like ifs and whiles and loops and procedure calls and so forth. But in those days, that's not how programs were written. There were lots of go-tos. Sometimes people referred to these programs as bowls of spaghetti, with the idea was that there were so many sort of pointers going this way and that, you couldn't figure out what was going on. What Dijkstra said in this paper was that it's not easy to get correct programs, and we really would like to be able to reason about the correctness of programs. And to do so, what we do is we reason looking at the program text. But what we're looking at, or what we're reasoning about, is what happens with that text when you actually run the code. And his argument was it's much easier to reason from the text if the structure of the code is such that it matches the text as closely as possible. And with go-tos, it didn't often, but with well-structured control structures, it would. This was a very controversial paper. And there were two reasons for that. One was people were insulted because he was saying go-tos mean bad programs, and they were saying we write good programs with go-tos, which is perfectly possible because you can write a good program even in a lousy programming language if you're well disciplined and use it properly. And then other people were concerned that go-tos were necessary, that you would never be able to have an efficient program if you didn't have it. And that had to do with inadequacies in the programming languages at the time, and the fact that compilers then were much more primitive compared to what we have today, so that lots of kinds of optimizations were not being done. At any rate, this is a very good paper, and it had to do with reasoning about the correctness of programs, which clearly has to be what you're going to do if you're going to be able to build programs that work. Okay, the next paper on the next slide is a paper by Dave Parnas, and Parnas was interested in modularity. In this particular paper, he was talking about the interface that a module provided to the rest of the system. And he said in this paper that the connections between modules are the assumptions which the modules make about each other. And what he was getting at was that in order to have a complete description of the behavior of a module, you need to capture everything it does, all the ways it interacts with the rest of the system. You couldn't limit it just to these are the arguments I pass into a procedure and here's the results, if there were other ways in which it communicated. And so he's really getting at, what does a specification say if you wanted to write a specification of the module? He didn't really say what modules were in this paper. And in fact, in another paper, he wrote it about the same time. He said, we know we need modules, but we don't know what they are. So that was kind of the state of the art. Okay, next slide, please.
Yep.
So here's modern modularity, what we all understand today. We know a program is a collection of modules. In fact, in modern programming languages, we actually compile them independently and so forth. Each module has an interface that it provides to the rest of the system, and we know that we describe that through a specification, maybe not a formal specification, maybe an informal one, but nevertheless a description of what it does. And then it has an implementation written in the code of some programming language. And what's really powerful about this idea of modularity is that if you do it right, you can argue independently about module correctness. So I can look at the code of the module and I can look at its specification and I can create an argument that says, this is why this module is a correct implementation of that specification. And you can do this even if the module makes use of other modules, because you don't have to look at the code of those other modules, you just look at their specifications. This is something, it's very similar in structure to a mathematical proof, if you think about it, where you have a little proof of some statement that you're interested in. In this case, it's this implementation matches that specification. And in that proof, you use lemmas. You refer to lemmas that are being proved elsewhere. Those lemmas here are proofs that those other modules match their specification. In fact, when I think back on this today, I think, gee, it was really good I was a math major, because obviously it really informs the thinking here. And of course, everybody was talking about this. And a good example is a sort routine where the specification says when it returns, it's the same array with the same elements, but they've been arranged in the sorted order. And then if you look inside, it's one of the many many ways of doing sorting that have been invented since then. Next slide, please.
Yep.
So that's today. This is what was happening in 1970. We knew we wanted it, and we understood its benefits. And local reasoning, which is what I just described, was really the key thing that we wanted, because everything flows from that. If you have local reasoning, then you can have independent development where different programmers are working on different modules simultaneously, but in the end, these modules can make use of each other in a reasonable way because they've all been, reasoned about independently and they all match their specifications. And you also have something called modifiability, which means that I've got an implementation of a module and I decide it's inadequate for some reason. Maybe it's not fast enough. And I can rip it out, put a new implementation in, and all the code that made use of that module isn't affected by this. It doesn't have to be re-implemented. It can just be as it is. So we knew we wanted this. We just didn't know what modules were. Next slide.
Yep.
And part of the problem was that we didn't have module mechanisms. We didn't know what modules were. And all we had to play with was subroutines or procedures. That was the only modularity mechanism that existed at the time. And it just wasn't powerful enough to match the things we knew wanted to have as modules, like file systems and databases and other complicated things. Okay, so I read all those papers and I realized, next slide, please,
Yep.
that when I was working on that Venus operating system, which was my previous project at MITRE, I had actually invented a modularity mechanism that had much more structure than what people had been talking about. Now, what was going on in those days was that the way programs were implemented was there typically was a bunch of global variables. And then there was a lot of code, and maybe there were go-tos or maybe there were procedure calls, but there was a lot of interaction between the different pieces of the program going on through the use of these global variables. And I thought that sounded like a recipe for disaster. Mind you, I'm coming out of doing my thesis. I did a lot of programming in Lisp. Lisp is a modular language. At any rate, I thought that's a bad idea. This working through global variables is a mess. And so I invented what I called partitions. Next slide.
Yep.
And there it is. I said there's no global state. All there are these separate modules I called partitions. Each one of them owns a part of the state. The other partitions are unable to actually access what's inside this partition, but they can influence by calling a set of operations that the partition provides for use by the other modules. So I wrote this up, and then I moved to MIT. Next slide.
Yep.
And I moved to MIT because partly because I had written a paper on the Venus system, which I submitted to SOSP, the top systems conference, and I was a prize paper there. But at that point, people were starting to look for women on their faculty as well. So I was hired to MIT. I was the first woman in computer science. And when I joined MIT, there were 10 women on the faculty out of a faculty of nearly 1,000, just to give you a sense of what things were like in those days. Okay, so I moved to MIT in 1972, and I was absolutely, next slide, please,
Yep.
obsessed with this question of what are modules? So I had read all these papers. Each paper individually was very compelling. They would describe a design for a system, and you could see that it was a good design and so forth. But when you tried to apply what was in that paper to some problem of your own, where you were trying to do your own design, it all sort of fell apart, and you just didn't have anything to work with. And so I was trying to figure out a way to bridge this gap. And I thought about it, probably, in the middle of the night, and I know while driving to work, and, just thinking about it all the time. And sometime in the fall of 1972 or the early part of 1973, if you could go to the next slide, I realized that I could think about partitions as data types. So if you look at the next slide,
Yep.
You can see the match. I mean, there's a partition. It's got this hidden state inside it that it's responsible for. It has a bunch of operations. So all I'm saying is some of those operations allow you to construct objects of the new type. Other operations are there to interact with objects that already exist. I mean, it's exactly what we think of as a data type today. But the connection I made, if you could give me the next slide, was I knew it was very important. And the reason it was very important is because it links modularity to design. You can't design a program by saying, I just want a bunch of black boxes. But you can design a program if you think about abstractions. And having this new kind of abstraction, which matched the kinds of things we were looking for, like file systems and so forth, meant that we had this new thing that we could use while we were designing programs that was going to make it much easier to do design. And then also, by the way, I had this set of rules about what modules could do that would make it much more possible for us to do local reasoning. So I knew this was a big step forward, just having this connection between a particular type of module and a notion of abstraction. And I also thought that programmers would have no problem understanding how to apply this notion of abstraction because they already understood data types. The programming languages in use always provided a few data types. They didn't give you a way of defining new abstract types, but there were some built into the language and programmers already understood them. So I was sure they'd be able to invent new ones. But for this to all hang together, it required programming language support. Next slide, please.
Yep.
And so I took the next obvious step of trying to figure out what that programming language would be like. And I did this jointly with Steve Zillis, who was a graduate student at MIT at the time and also an employee of IBM. And Steve had similar ideas. And I should say that that idea of connecting modules to data types was kind of floating around in the literature, waiting for people to pull it out. It's not surprising that more than one person had the same idea at about the same time. So Steve and I, next slide, please, worked together for several months. And of course, one of the things we did was we read a bunch of literature, and I want to describe a couple of papers that were important. This one by Jim Morris. Jim was very interested in this question of local reasoning, and he wanted to find the rules that would make it work. Next slide. So what Jim said, first of all, was code outside the module must not modify the data managed by the module. In other words, and this is an obvious rule, because if the code outside could be in there manipulating your data, then you have no local control over it. And so how can you possibly reason about the correctness of your code? But then Jim also said, next slide, that it shouldn't even observe it. And the reason it shouldn't observe it is for the modifiability desire. You know, if you want to be able to rip out an implementation of a module, replace it with a new one, but you have using modules that are actually depending on your current implementation, then you're going to have to re-implement them too, so you don't get locality. And Jim also went on to look at an enforcement mechanism that would guarantee that these things were followed. He didn't know how to do that, so he basically used a kind of encryption where objects, as they moved out, were encrypted using a secret key, and this meant that on the outside they were incomprehensible, and if they came back in, you could check to make sure they were still in good shape. Okay, so that was a good idea, but obviously one that wasn't going to fly in practice. So next slide, please. Okay, so that's Jim's idea. The other one I want to mention is this paper by Ole Johan Dahl and Tony Hoare, Hierarchical Program Structures. And this is a paper about Simula 67. Simula already existed then, and Simula, as I'm sure everybody knows, had classes and subclasses. This was a major input into the work that Alan Kay did on Smalltalk, and then that whole notion of inheritance that is an important part of the object-oriented way of doing things. Steve and I looked at this paper, and although we could see that this fit a notion of data type, we decided we didn't want to base a programming language on this because there was a lot of block structure here with, you know, inner code being able to make use of the private information of things on the outer code and so forth. And we felt it would be easier just to start from scratch and not try to use Simula 67 directly. And we also felt that inheritance was kind of a side issue and not one we wanted to cope with right then. Next slide, please. So Steve and I worked for several months, and at the end of the summer of 1973, we had a paper that we submitted for publication that had a sketch of a programming language. Next slide. And it basically explained abstract data types as we know them today, and also provided a little sketch of a programming language. The important part was that we wanted to enforce encapsulation, not by using encryption, but through type checking. Okay, next slide. So then I did the obvious next thing. I went ahead and designed and implemented a programming language. And this work was done jointly with 3 graduate students who joined my group in the fall of 1973, Russ Atkinson, Craig Shafford, and Alan Snyder. Steve was a participant in the design, but he was working on his PhD thesis, which was about specifications of abstract data types. Next slide. Okay, so, that's just a picture of me in 1974. I didn't take pictures. In those days, people didn't take pictures like they do today anyway, because, you know, you had cameras and so forth. And I'm sitting in my office with Jack Dennis talking about some technical problem. Next slide, please. Okay, so designing and implementing a programming language was the obvious next step. But I also had a well worked out rationalization for why to do this. The first is a programming language is a mathematical object, and so you can't be imprecise when you put mechanisms into a programming language. And I felt that part of the problem with the papers was that they were very imprecise, and this was one of the reasons people were having trouble applying the ideas to new systems. And then, of course, the programming language is a tool, and what we were really trying to understand here was whether a programming language with abstract data types would really work in practice. And for it to work in practice, it has to be convenient to use. It has to have enough expressive power that people can write what they need to write in a convenient way. And of course, it better perform well. Next slide, please.
Yep.
Okay, so I'm not going to say much about Clue, but I did want to give you a kind of a high level idea of very basic stuff that was decided early on. So first of all, Clue was a collection of modules that were compiled independently. And furthermore, the objects were in a heap. And if you think about this, you can see this coming directly from Lisp, where we had a heap with garbage collection, and all we had was procedures, but they were all compiled independently. On the other hand, Clue had algo-like syntax, which is the kind of syntax we use today, with block structure and variable names and so forth, whereas Lisp used all these parentheses, which I found very unattractive. And we had static type checking to enforce, to find errors, because when I was working on my PhD thesis, it was so annoying when I would spend several hours finding a bug that I realized could have been found by the compiler if it had done some type checking for me. So the interesting thing and then no concurrency, because I felt that would be a major distraction. It was hard enough to work on a sequential language. No go-tos, because I thought Dijkstra was right. No inheritance, because I felt it was a distraction. One thing I wanted to say here was that deciding that the language was heap-based went against what was sort of the main view of people in the programming language community at that time, where they thought of pointers as being evil. And I mean, it was really a different time, and it's kind of hard to think that it's like that then and what it's like now. But from the point of view of data abstraction, this was a very important decision, because what it meant was that when you compiled the code of a using module that used some data abstraction, you didn't have to know how big the objects were, and you didn't have to worry about allocating space for them on the stack, because the objects were in the heap and all you needed was a pointer. Next slide, please.
Yep.
Okay, so Clue took a long time to design, and the reason was we had a lot of work to do. First of all, we had to invent a mechanism for implementing data types, and these were similar to classes. We called them clusters, and cluster is where Clue came from. That's the name, the first 3 letters of cluster, but just think of them as classes. There were some differences, but they're not very important today. But then it turned out there was a lot of other stuff we had to work on, and this has to do with what programming languages were like then as opposed to what they're like now. So we realized we needed a way of iterating over data types that were collections of things. So if you have a set, or a bag or whatever, you would like to collect things into your collection, and then you'd like to iterate over the collection, looking at what's there without destroying it. And so we had to invent a mechanism for this because there wasn't one. And we invented something we called iterators, which were sort of like the generators we use today. And then exception handling at that time was a research topic, and there wasn't really any language around that had a good one. And so we spent a lot of time designing an exception handling mechanism, which was somewhat like the modern ones that are used today. And then in some sense, the hardest thing was polymorphism or generics. In those days, there wasn't any, and it isn't a big deal for a typeless language like Lisp, but it is a big deal for a strongly typed language. And it seems to me, looking back, that even if you didn't have data abstraction, it was kind of a pain, because it meant if you defined a sort routine for an array of integers, it wouldn't work for strings, and then you'd have to re-implement it to have it work for strings. But you can see it's totally impossible if you're in a world where new data types are being invented all the time. And I just want to show you a little bit about what our generic mechanism was like. This was the hardest technical problem we dealt with. Next slide.
Mm-hmm.
Okay, so here's a parameterized cluster for set. because obviously you would like to have one definition for set, and you wouldn't want to have a new one for, one for integers, one for strings, and so on. And you can see it's parameterized by a type. And what's on the those little blue things, those are the names of the operations that the cluster provided. However, the problem with parameterized types is that they often have certain constraints on what parameters are legal. And so the question was how to do this in a way that could be checked at compile time. And our solution, next slide, was something we called a where clause, which listed the operations that were required. In the case of set, all you need is an equality operator. And that says that the type has to have an equal operation, which is a procedure taking in two t's, returning a Boolean. Obviously, associated with this would be a specification explaining the meaning of equality. And next slide, please. What you can see from this is that you can do type checking on both sides. So when you're compiling the code of the set, you can make sure it only uses the things listed in the where clause. And when you compile some code that uses the set, you can make sure that that type satisfies the where clause. And notice this is really sort of like what's in Haskell today, Haskell classes. Okay, so that was our mechanism. And that's sort of it for Clue. Next slide. Okay, so I finished Clue sometime in the late 70s. And then I jumped into distributed computing. I read a paper by Bob Kahn talking about the glories of the internet and wouldn't it be nice to have distributed programs. Nobody knew how to build them, and I thought that's a great problem. And so I started working in distributed computing. I did a bunch of interesting work there, including a lot of programming language design. I'm not going to talk about that. Next slide, please. But I never lost my interest in programming methodology. And one of the things I did was developed a course at MIT. It was a second programming course where we assumed the students knew how to write code, but we were teaching them how to design large systems. So we taught about design, we taught about how to reason about the correctness of code, local reasoning, and so forth. Most of that work was done jointly with my colleague, John Guttag. Next slide, please. And then along with this, I'm going to talk a little bit about my work on type hierarchy, another thing that came along in sort of the methodology domain. But what I meant when I said I never lost my interest, I was always thinking about how do you reason about programs and so forth, because that's such a fundamental problem in computer science. Okay, so what happened with type hierarchy, next slide, is that I was invited in 1986 to give the keynote at OOPSLA, which is, the main conference on object-oriented programming. And I decided that was a good chance to read the literature about Smalltalk and other languages that were being developed on the West Coast. So I was an East Coast group, and see what was going on with that community of language developers. So I started to read the literature. Next slide. And of course, Smalltalk provided inheritance. They picked up that idea from Simula 67 and made it the basis of the language, although they also abandoned the block structure, except that one class could borrow from another and put the objects in the heap. So it was, in a way, sort of the same choices that I was making in Clue. And I discovered in these papers that inheritance was being used, first of all, for its original purpose, which was implementation, so that a subclass could be implemented by borrowing from the superclass and just changing and adding a few things. But people were also very interested in something they called type hierarchy. And that wasn't something I had thought about before. And I thought that was very interesting also. But what I discovered, next slide, was that people didn't understand what it was. In fact, as far as I could see, they were all wrong. And I remember specifically a paper I read that claimed that stacks and queues were both subtypes of one another. And this was clearly wrong, because if I wrote a program that expected a stack, and instead I was passed a queue, and after all, this is what they wanted to do with subtyping. They wanted to be able to pass objects of the subtype into code that expected the supertype. If I was passed a queue instead of a stack, my program was unlikely to work because I expected LIFO and I was getting FIFO instead. So something was not right about this. And honestly, all the work I had done on that course of MIT and all that talking about specifications and correctness and rules of inference and so forth, it meant I was thinking about data types in some sense differently than what they were in this community, where they had a tendency to describe the subtype by talking about how its implementation differed from that of the supertype. So the fact that I was thinking more from the specification point of view gave me a sort of a step up on what was going on there, and I was able to see what the problem was. And so, next slide. In the talk at Uppsala, I defined what has come to be called in the research community behavioral subtyping. And simply I said objects of subtypes should behave like those of supertypes if used via supertype methods. And I put behave in red because what I'm really talking here is the semantics of the type. And of course you need syntax to match also, but you really need behavior. That's why stacks aren't a subtype of queues and queues aren't a subtype of stacks, because they behave differently in an important way. This is also a minimal definition because it only is that you use it in a context that expects the supertype. It doesn't have to behave just like the supertype. It just has to behave enough like the supertype that it'll work in such a context. Okay, continue. Next slide, please. Okay, this came to be called the Liskov substitution principle. And I didn't invent that name, but what happened was in the 90s, I got an email from someone saying, is this a correct definition of the Liskov substitution principle? That's when I discovered that there was such a name. That's when I discovered there were huge groups of users trying to figure out what exactly the rules were. Next slide, please. Mm-hmm. And then Jeanette Wing suggested in the 90s that we work together to come up with a formal definition of behavioral subtyping. So that paper in Topless is the real definition. Okay, next slide. So we're almost done. Okay, so when I got the Turing Award in 2009, I hadn't been thinking about this stuff for a long time. And so I started thinking about modularity and abstraction again. And I realized that the world had changed while I was not paying attention. And in fact, modularity based on abstraction is just the way things are done now. I even discovered that my graduate students didn't know there was a time before that there was data abstraction. They sort of thought this is how it is. And in fact, my husband was on the internet every day and he found a comment on there. You know, the internet is not a very kind place. And this particular comment said, why did she get this award? Everybody knows this anyway. But in fact, you know, there was a time when nobody knew it. And due to the work that I did and the work of many others in the program methodology community, this is how it is now. And isn't it lovely? That was a great compliment. Next slide. So I'm all finished. Thanks for listening.
Of course. Okay. 1 second here, guys. Okay. So thank you very much, Dr. Liskov, for your extremely insightful presentation. Can I get a virtual round of applause for Dr. Liskov, everyone? Come on, guys. Do not hesitate. Let's go. Okay.
That was very, oh, look at that. That's great.
Okay, and then, so Dr. Liskov, thank you so much for taking your extremely valuable time to educate us students. Dr. Liskov, I'll be following up with you shortly to inquire where we can send you our official Georgia Tech merchandise and various other speaker gifts, including chocolates, of course. We would love to extend our deep appreciation for your time and your willingness to speak with us. And thanks as well to everyone in the audience for your attendance. And we'll see everyone next week. We have Dr. Nir Shavit. I think he's also MIT.
He is, yep.
So
we also have an interesting question in the chat here. First of all, thank you, Dr. Liskov. Really appreciate you giving us your time. Marina is asking, how did your peers share their programming language ideas with each other prior to the internet?
conferences, and also there was a DARPA. DARPA is the defense agency of the government that was sponsoring a lot of this research. We used to have a small group of us used to meet every 6 months or so. That was the people that were interested in data abstraction. One of the things that's really interesting about those days is we weren't communicating very much between the East Coast and the West Coast. That's why, when I said in the 80s, I decided to find out what was going on with Smalltalk. I knew about it, but I wasn't really communicating with that community. And they were not sort of I don't know, it was just a slightly different community. And then when OOPSLA came along, of course, then everything moved into that. But as you know, there's OOPSLA, and there's several also programming language community of other conferences. So, the conference structure has grown since the early days.
Okay, very cool. And we have 6 people who have said that this is their favorite talk so far. So that's awesome. Yeah. Anna says that she actually learned Java from your book and fell in love with it. And this way of thinking specifically since reading it. And we have a lot of compliments rolling in.
What other questions do we have?
Yeah, we have another question by Gary. Gary's asking, do you have an opinion about the state of programming languages today? Are there any languages today that you are excited about in terms of new kinds of problems that the languages are helping solve?
I am not really in the programming language community. What happened was I moved into distributed computing, and most of the work I've done, it's not true because I did programming language work, but I was really very interested in some of these distributed systems, protocol stuff that I was doing. So I can't say that I have a favorite language. I think that there's been some interesting work in programming languages trying to make it easy for new programmers to use the system. But one of the problems with some of those languages is they don't enforce encapsulation. And that means that unless you're disciplined, the code on the outside can be mucking around with what's going on inside of a module. So, of course, if we use these courses in a teaching environment, it's very important to teach the students not to do that. But I wish that kind of encapsulation were enforced, because when you're working on a big system with a lot of other people, the quality of the code is the weakest programmer in the team can screw things up. So an encapsulation helps to keep from these sort of errors from being made. So I wish that was maybe more enforced. I also think I've done quite a bit of parallel programming in some of the recent work, and my experience has been that you should just leave the modules alone and let them do whatever they want. Because if you have locality, then inside the module, you know exactly what's going on with the concurrency, and you can do all sorts of clever things. You can allow these operations to run in parallel, and you can know that, you have complete control, and so you can do lots of clever things. So I'm not sure that adding extra stuff to a language that enforces this or that is really the way to go. I think if you had encapsulation, you could just let it alone. But I'm speaking as a non-member of the community, so it's not like I'm totally up on everything that's going on. Yeah.
Amazing. We have a couple extra comments rolling in. There's a lot of engagement from the audience. We have someone, as Azad says, brilliant, concise, lucid presentation. Lynette says, thank you for spiking my interest in programming again. Marina is saying that they've also found a similar geographical divide among other historical fields of academics.
Yeah.
Herbert is.
Yeah. I just want to say, airplanes were not what they once were. It was a much bigger deal to fly from one coast to the other. definitely in the 60s and the 70s, so that made a big difference. You weren't as willing to go traveling around the way you are now. And of course, the internet has made a huge difference. But there was file transfer.
Yeah.
Yeah.
Herbert is asking and mentions that you said that a fundamental is that a module must be precise in respect to functions, so deterministic, but we face increasing complexity and massive increase of information volumes. So how can this still be maintained, or are we forced to accept a degree of probabilistic behavior?
I did not mean that they had to be deterministic. All I meant was that, first of all, I was talking about a programming language. I just said it had to have rules that were precise. But then when I was talking about specifications, I wasn't limiting what the specification could do. So, you could have something that had a probabilistic behavior and your specification would explain that was what was going on. So I don't think I'm limiting at all what a module can do. All I'm saying is the module is a kind of a black box, a real black box, and it's in control of itself. And there's a specification that describes, as Dave Parna said so many years ago, the complete behavior of the system and how it interacts with the rest of the system.
Yeah. Amazing. We have another comment. Thank you so much, Dr. Barbara. I sort of come from a similar place. I'm getting into computer science from a long career in math and can't help to feel a bit out of place. I'd love to hear your perspective on this coming into computer science in what was back then a male-dominated field. Did you feel that pushed you to study or work harder, or did you feel that you need to prove yourself then?
Oh, okay. So I don't think it caused me to work harder. What it did was, when I got my PhD from Stanford, I would have liked to have gotten a faculty position, but I didn't have any good offers. And in truth, the old boys network was in full swing, but I was also very naive about what it meant to apply for jobs. On the other hand, there also was not much talk about what you were supposed to do. So anyway, I didn't have any good offers. That's why I went back to MITRE. There I could do research and I was changing fields. It's discouraging when something like that happens. So I had to persevere. So, you sort of have to keep on going. It turned out that going to MITRE was actually really good because I was making what was a pretty massive change in research direction. And I was able to do that without the extra things you have to do as a professor, where you teach classes and, you're on committees and there's a lot of other stuff. So I was able to really focus on research for time. And when I look back at my career, what I see is happy accidents. So I got into computer science by accident. I happened to go to MITRE instead of going to a university. When I got my PhD, that was actually good, but of course, I couldn't let it discourage me. So it's sort of, you keep on going. And I do think that certainly when I was first on the faculty, the women who were being hired, I thought were probably more distinguished than the men because you had to pass a higher barrier. I don't know, I think things are better today, but they're still not perfect. So you just persevere. But this thing about opportunities coming is what happens in every career, So I didn't get a job as a mathematician. I got a job as a programmer. That was, a door opened, a door closed, a door opened. And then when I got my PhD, a door closed, a door opened. And when I talk to people at MIT, the ones who come back for their 50th reunion, what we call the red jackets, because they wear red jackets. I hear stories about their careers and they're very similar. Some of them are doing exactly what you would have predicted when they got their PhD or their bachelor's degree, but many of them have gone off in completely different directions. So I think perseverance and taking advantage of opportunity and paying attention to what you're good at and paying attention to what you like to do, that's just how you should be. And don't worry too much about. I probably shouldn't say that. Some people have a harder time than I did, but yeah.
That was incredibly insightful advice. Thank you. So essentially follow what you're most passionate about and interested in a sense.
And what you can do, because
Yeah.
I've had students at MIT where I've had to try and gently persuade them to switch majors, because you can't do something, you have to be able to do it. You have to be good at it.
Right.
Otherwise, we're going to really, that has to do with something innate about what your talents are and what everybody is good in different ways.
And also blow the boys out of the water. That's what you got to do.
So we have another comment here by Atharva saying, it was an honor listening to you. I was wondering what your thoughts are on dynamic typing languages like Python and JavaScript. I've always loved strongly typed languages due to easier debugging.
I think, and again, I'm speaking as somebody on the periphery of the programming language community, that a combination of static and dynamic is a good idea. It's actually much easier to write in a dynamically typed language, but there's no reason why the compiler can't be filling in the gaps and producing a written form for your language that has the actual types in it. And that way, later when you go back and look at your code, because I think one thing people forget is that code is read much more than it's written. And it's often read by people who didn't write it. And what you'd like is a written form that has the real thing in it, the full rules. So some combination that makes it easy to write, but also ends up with a form that has everything, so it's easier for people to understand. That's a really good idea. And while I'm at it, I would love to see compilers doing something about the Liskov substitution principle. I mean, we've made huge strides on program verification, but I would really like to be certain. I would love to be certain that the code I'm calling matches the specification. And I would really like to be certain that something that purports to be a subtype of something else really is. And this is a program verification problem. In the case of subtyping, it's really a program verification problem of the specifications. And then, of course, a program verification problem for the code versus the specification. And I think, great strides are being made here, but that would be a big help to be certain of that, because I've had the experience of looking at code where you could never be certain whether the objects were behaving the way you thought they should, and it really makes it difficult.
Yeah, hopefully somebody hears this and goes ahead and dedicates their life to that. So another comment from Manish says, thank you for the great talk. You mentioned about working with John McCarthy. If possible, could you please talk something about the Lisp programming language and the idea behind it?
Well, so Lisp is based, I probably can't say anything very specific. Lisp is based on the notion that your main data type is a list. And there are operations on lists. I mean, it is a data type, to create a list, to add something to the list, to get something off the list, just what you'd expect. And it's a very flexible data type. So, they were able to build all sorts of programs using that data type. And then, as I said, it had its objects in the heap. That made it very, very flexible. And it had modularity. I mean, you really did write your Lisp programs by writing one procedure at a time, and you would compile your procedure, and then you would compile your next procedure, and it could all be done independently. So it was very foresighted compared, to where we are today, where that's very common. I mean, that is how programs are built today. You have modules, you compile them separately, you put them together, So John McCarthy was very broad. I mean, not only did he design Lisp, he invented time sharing. He was working on program verification. He's also working on artificial intelligence. So he was sort of a man of all things. Yeah.
Amazing. And we have, just about 2 more comments here. Onur says, it's a great privilege to be here. Thank you, Dr. Liskov, for all the contributions you have made. Lynette says, was it easy to switch from programming methodology to distributed computing? How did you get started? I'm in a similar space moving from programming to AI.
I got started there wasn't much literature. I mean, it was early days. But of course, I was reading everything. And my first project was a programming language project where I basically took Clue and made it into a distributed system where the units of distribution were objects. And it worked out very well. So I don't know, I've changed many times. And I think that what happens is you see something interesting, you start reading the literature, it has to be something you're interested in that sort of matches your abilities, and somehow it works. I have no magic rule here. Yeah.
Okay, amazing.
Do we have more questions, Parsa?
No.
Okay. So on that note, let's get another round of applause. Come on, guys. Let's go. All right. Virtual round of applause, of course. Okay.
Maybe.
There we go. Let's go. Okay. So again, thank you so much to Dr. Liskov for taking your extremely valuable time to educate us students. Like I said previously, I'll be following up with you shortly to inquire where we can send you your chocolates and official Georgia Tech gear. Again, we just want to extend our deep appreciation for your time and your willingness to speak with us. And we thank everyone in the audience for your attendance. And we'll see everyone here next week. Dr. Nir Shavit. And let's go, guys.
Okay. Thanks very much. I enjoyed it. Bye-bye.
Of course. Bye.
Yeah. Bye. Okay.
Let's go.